Okay, so I don't know if you're familiar with, if anyone's familiar with survival analysis in the first place, but survival analysis is basically dealing with data that is censored. So we're taking in the time until a certain event happens, and where patients are not always seen until the event happens. So there's the possibility of a patient being censored. So we don't know what exactly happened during this time because they exited the study for different multiple reasons. So for example, in the data set that we're going to be working with, we're taking a very typical data set that is used in most literature, and it's called the Colrec data set. And it comprises of around 6,000 patients diagnosed with colon or rectal cancer. And there are 7 variables that indicate age, year, and sex. Status. Status is going to be for censorship. So if the patient is censored or not. So if the event was observed or not. The event here is, we're talking about death because it's survival analysis. So we are observing the death of a patient. The follow-up time or survival time, cancer stage, and cancer site. And it's sourced from the Slovenian Cancer Registry. And what net survival is, or relative survival analysis, which is the main field that is that the package is constructed upon, it takes a reference rate table, which is here the Slovenian mortality table, and it compares the patients from the cancer data set to the general population mortality table. So it is expected of a normal person. So what a mortality rate is expected of a normal person, undiagnosed with cancer person, and people from the cancer data set. So the mortality table includes information on age, year, and sex. And with these 3 variables, we are able to identify the patients from the data set and their expected mortality rate on a populational level. And it's extracted from official census mortality rates. So when we're dealing with any sort of data, the first thing is we're going to take a look at the variables and what they're telling us. And so here we can tell that most of the patients are aged between 60 and 80 years old. And the follow-up time, so the survival time, takes a very, very quick dip. So within the first 5 years, most patients are passing away. And now to look at it from a net survival point of view or a relative survival point of view, we're going to apply the power per mai estimator. And the power per mai estimator is basically estimating the excess mortality rate. And for the excess mortality rate is the mortality rate specific to people with the given cancer or the given disease, compared to the populational mortality rate that is given from the mortality table. And so with this interface, it resembles exactly the one that already exists in R, because there's a package that does the exact same thing in R. And so the interface resembles exactly that. That way, new users can be easily accustomed to using Julia because it's almost the same as the code in R that already exists. So by running this, we get a table with the net survival probability in daily intervals. So 1 day after the study, what is their mortality rate, 2 days, 3 days, etc. And for a better visualization, we can tell that the graph on the left looks a little bizarre. So within around 11 years, the survival probability starts increasing, and then our confidence intervals are way too large. This also is apparent in the R version. This isn't an issue from Julia or from the package. This is an issue with the estimator. The estimator becomes less accurate with time, because here we're going to actually see a bit more on the explanation here, but the hypothesis is that we are losing a lot of patients due to cancer, and so most patients are dying from other causes, and it's making our estimator a little unstable. And when we're focusing only on the first 5 years, we get a more coherent or logical survival probability that is constantly going down. And around 5 years, we're already at under 0.5 survival probability. So let's find out why this estimator is exactly losing its accuracy. And this is where we run a NESI function. A NESI function is a function that allows us to view the estimated lifetime and the estimated sample size. So what we're expecting to see people dying from other causes due to the mortality table, either in sample size or in lifetime. So for example, when we're separating our patients from young and old, we can see that around at the end of the study, we're expecting to lose almost 3,000 older patients and less than half of the younger patients. This is strictly based on populational data and not cancer, and not the cancer data. So what we're expecting if they didn't have cancer, how would the sample size look like? This is to prove, again, that older patients are the bigger majority of our study, and they're also dying from other causes, which is making our estimator less accurate because they're dying from other causes and not from the cancer. And so the estimator that calculates mortality based on the cancer is less accurate. Same thing here, when we're drawing it on a graph, we can see that the slope for the older patients is a lot stronger. So we choose to censor the data around 5 years because we still have enough data on the older and the younger patients as well. And to then again prove the loss of accuracy at around 11 years, we can tell that the expected years left for the two groups, for the older patients, we have around 10.2 years left. And so at around the 11-year mark, it becomes much less accurate because we have a lot less data. Another cool function in the package is the crude mortality function, which allows us to separate the causes of death in terms of mortality. So, for example, this is the output that we get from running this function, which is the crude mortality function. So out of the 64% patients that have died, which is the FO, so more overall mortality, out of the 64%, we have 53% that is due to the colorectal cancer and only 11% due to other causes. This is at the 5-year mark, and the specific time can be specified, and so we can check at any given point in time how much of the percentage of death is due to the cancer and how much is due to the population, to other causes, to any other cause. Lastly, we have a log rank type test that is also integrated into the package. And also its interface resembles a lot the one in R. So it allows new users to easily integrate or easily use the Julia version of it. It's the cfeotest, which is specifically designed for relative survival analysis. And it allows us, just like any typical log rank type test, to check if the variable has significance to the study. So here we notice that the age and the stage of the cancer are relevant to the study. And the conclusion is a very elementary one, but it's more of an example to show how to use the package rather than an actual real example. Here, the conclusion is that the older and the more advanced the cancer stage is, the lower the risk of survival, which is very logical. And so in conclusion, I wanted to make a point on the JuliaServe organization that's on GitHub. And basically, this organization was created to house all packages related to survival analysis, not just relative survival analysis. And it's growing, it's expanding. We are adding as many packages as we can and as many functionalities to the packages as we can. Yeah, that's it. Just a little quick summary. There is the QR code, so you can check out the GitHub for the NetSurvival package. And just a quick summary, survival analysis deals with censored data where the variable of interest is the time until a certain event occurs. Most of the time it's death, but it can be applied to a bunch of different fields. In some specific cases, the exact cause of death is unavailable or unreliable, which is why relative survival analysis was built or created in the first place. So our Julia implementation is much easier to read and more concise and faster than ours, which was the main interest in creating one in the first place. And we hope to expand the Julia Serve organization and to include as many helpful functionalities through it. Thanks.
Awesome. Thank you so much for presenting today, Reem. This was fantastic. I guess I'll do like an emoji reaction clap. It's a little hard to clap on Zoom, but thank you so much for presenting today.
Thank you.
Yeah, and we'll open the floor here to if there's any questions from the community just about the software or just survival analysis in Julia in general. I'll start maybe with like a smaller question, which is, I know that you had worked on this, over the past several months or so. I guess, my question is maybe where do you see maybe NetSurvival.jl going in the future, or what work remains to be done, I guess, kind of when it comes to your particular package?
Well, in net survival, there isn't really a lot to be done because research is there hasn't been a lot of contributions. It's mostly just the net survival estimators and the logarithmic type tests that are associated. I guess any functionality that is suggested, we can try to implement it. But the main focus has been more on expanding the Julia Serve organization, where we're dealing more with a broader and less niche topic. So we're dealing with survival analysis, so how to make maybe Cox, I don't know if anyone's familiar with Cox models, how to make those faster or a bit more integrated within our interface, because there are other packages that are included that help facilitate everything within the organization. And we have a rate tables package as well that provides different mortality tables from different countries. So any contributions to that would be really cool.
Awesome. And I will open up the floor to if there's any other questions. If anyone has any questions here, feel free to unmute and you can go ahead and ask a question.
I have a question about the formula macro.
Yeah.
Yeah, like I'm not too familiar with R, but what is it doing? Or if you can explain it a little bit more.
Yes, so basically it's defining a formula. So we're taking the survival and the status and the time that are defined within a I'm gonna share my screen again, just hold on. So when we're defining a formula here, we're taking here serve is just it doesn't really do anything, but we're saying that in a survival context, we are taking variables such as time and status, and so kind of like a y, and it's being formulated within the variable. So so coefficients. So I don't know how to explain this in a clearer sense, but it's basically trying to formulate.
Is it like you're trying to fit age with variables time and status?
Yes.
Oh, okay. And in the formula macro, you basically identify that like wiggly symbol and split it in two, or?
I didn't necessarily understand the question. The squiggly thing is integrated within the formula macro. It wasn't something that we defined.
Oh, I see. Okay.
Okay. So kind of like the formula macro takes a right hand input and a left hand input and a right hand input. And those are defined as like left to the squiggly thing and right to the squiggly thing. These are defined within the macro cell. And this is the typical formulation on R and on Julia.
Oh, cool. Thanks. I guess it's something from statsmodels.jl, no?
Yes.
Or, oh, okay. Yeah, I didn't know. Thanks.
Okay, I think we have time for maybe just one more question. If anyone has a final question that they want to ask Reem. All right. I think that is it for questions. Well, Reem, again, thank you so much for joining today's call and being able to present. This was fantastic.
For
Yeah.
having me. And if anyone ends up with questions or checks out the organization and has anything to add, you can join me by email or even send a message on GitHub or on Slack. Anything is welcome. So yeah.